Good morning, everyone. Welcome to the first technical track of AI4Growth. We're starting with a couple of talks on hybrid AI. We have moderator Tom Dhaene from UGent, and Sofie van Hoecke, UGent, and Peter Hellinckx from UU Antwerpen. Without further ado, I will hand the word over to Tom Dhaene.
Hello, good morning, and welcome. In this session, we have two speakers. The first speaker is Sofie van Hoecke, professor at Ghent University and also associated with IMEC. Her research focuses on predictive maintenance, smart buildings, and predictive healthcare. And our second speaker will be Peter Hellinckx from the University of Antwerp. And his research focuses on data-driven control and Industry 5.0, mobility, logistics, and construction. So the first speaker will be Sofie van Hoecke, and after the session we will have the opportunity to ask some questions. Sofie, the floor is yours.
Good morning, everybody. I will give a talk on hybrid AI for prognostics and health management. Prognostics and health management, they are techniques that are designed to assess the health state of a system, to optimize the maintenance plan, and ideally shift towards predictive maintenance. It's a combination of detecting the current state of the system and predicting the next state or the remaining useful life of components. The system can be a machine, a process, or a vehicle. That doesn't matter for this presentation. Today, three approaches are currently used. One of them is physics-based models. In physics-based models, mathematical models are designed that describe the physics of the component to assess its current and future health. Challenges of physics-based models are that the performance of these models depend on the capability to accurately represent the healthy, but more specifically challenging is representing the failure and degradation phenomena. It's not easy scalable. These models are not easy scalable because they are system specific and each failure mode must be analyzed independently. And for some failures or faults like misalignment, dirt, and so on, modeling is quite hard or even impossible. An alternative approach is ontologies. Ontologies where an expert, a semantic technology expert, models concepts and relationships between these models in an ontology. When feeding it with data, it turns into a knowledge graph, and you can generate rule-based systems that fire when specific events occur. For example, here you see an ontology we designed in-house for anomaly detection, and then rules can be specified like presented on the slide. If a smoke observation, for example, exceeds a specific temperature, a value too high event is generated. This is also a knowledge-driven technique and has some challenges that goes with that. Namely, the same as before, the performance of these models depend on the capability to accurately model here the concepts and the phenomena. Designing these ontologies is quite challenging. It's difficult to construct and maintain, and therefore they are often incomplete. We designed an approach that starts from FMEA and fault tree analysis to model the failures and capture knowledge in rules. However, even then, you're only able to detect what is modeled, so one cannot use it to detect new unknown faults or anomalies. And then the third approach that is currently used today is data-driven models or machine learning. You have three different big categories of machine learning: the supervised, unsupervised, and reinforcement learning. Any of these start with collecting lots of data representing the problem you want to model. Then some pre-processing and cleaning of the data, training a model, testing it, and refining, further improving it. In our team, we have experience with anomaly detection, the top corner left, where you use matrix profile, autoencoders, or other solutions to detect the anomalies, behavioral, that has not seen before. You can also do fault detection, which are the big widgets in the middle of the slide. However, in order to do fault detection, labels are required of the different faults, so a machine learning algorithm can be trained to predict the labels. And the most interesting for predictive maintenance is of course remaining useful life, where you predict the remaining useful life of a component. However, that's again really challenging because you need labeled data until the breakpoint in order to train these models. So the challenges of machine learning is that you need enough data. And if you have enough data, then machine learning can learn correlations between the variables of the system and its health without having to know the physics of the failure, which is a benefit compared to the two knowledge-driven approaches I presented before. So each system and failure mode does not require a deep analysis of the phenomena. However, you need large data sets of healthy, and if you want to do fault classification, also fault conditions, and especially these labels are not always available. If you have enough data, you can shift even from machine learning to deep learning. Then you need big amounts of data, and if you can do this, it helps to solve more challenging problems on the one hand, but it can also alleviate you from feature engineering. Then you can just feed the raw data to the machine learning model, and it will learn the features itself. If you don't have enough data and you want to benefit from or you want to use the benefits of deep learning, you can use transfer learning, where you use a pre-trained model. For example, here in the top figure, you see deep learning models trained from scratch, and in the bottom figure, you use a pre-trained model that is, for example, able to distinguish cats versus dogs, and you can retrain it using transfer learning to use it for your car versus truck classification problem. So to summarize the three approaches frequently used today, if you want to do decision support powered by data analytics, my slides are for prognostics and health management. Peter will dive into the control, but so far all statements are valid for the both of us. Knowledge-driven approaches, they are based on evidence, guidelines, domain expertise, mostly white box. However, highly complex, difficult to construct and maintain, and therefore often incomplete. They are computational intensive and slow, and unable to handle unknown situations. On the other hand, the data-driven analytics or the machine learning, it learns patterns directly from the data. They are often black box. They depend on the availability of quality data sets, and you should be aware that your data set is representative for the problem at hand. Otherwise, you might induce bias in your machine learning model. They require minimal human intervention, no insights in the physics or domain. They are really efficient to execute, and they are able to handle with new situations. If you look at research in machine learning today, as it looks very promising, however, it largely emphasized general purpose learning and just getting more data, more computational power. For example, if you don't have enough data, you can do image manipulations. It looks like the same image to us for a machine learning model. However, these are totally different images. And this way, you can generate new data, get bigger data sets, and use more advanced machine learning. However, in our team, we also wrote a publication. It's presented here. You should be careful with oversampling. The solution with the cat it's quite safe, but if you do this with patient health record data, time series, it's more challenging, and one should be aware that you don't have data leakage, because if you do oversampling in the wrong way, you will receive overly optimistic prediction results, resulting in a nice machine learning model on paper, but useless in practice. If you don't have the according data in your data set, you will also have problems when the machine learning tries to, is confronted with this new situation it didn't saw in the data before. For example, here you see a model that is learned to detect buses, cars, trucks, and so far. It didn't it only saw normal buses, not in this non-canonical orientation. So it's not able to detect this is a bus, and it predicts it's a snowplow. So machine learning, the solutions we have today, they are still narrow intelligence. The machine learning models are trained for a really specific job, and they are not robust or transferable to even modestly different circumstances with extensive retraining. Similar to the bus example of some slides before, an AI model that is trained on thousands of chair pictures will not be able to recognize this upturned chair if there were no upturned chairs in its training set. If we translate this to prognostics and health management, it means that if you train an anomaly detection, fault detection, or remaining useful life model for PHM in, for example, compressors, if the model is trained in Hoste's fort, where degrees are minus 7 degrees, that model will not work for compressors who are in more used in hotter environments. Because the context changed, the machine learning model cannot transfer what it learned from one context to another. Hybrid AI brings a solution to many of the shortcomings I presented in this introduction. And I will present you 4 different approaches on how we do hybrid AI within our team for different challenges. The first hybrid AI solution is where we combine and use knowledge-driven approaches and machine learning approaches side by side to solve the lack of labeled data. And if you have missings in your knowledge model, if it's incomplete, by doing this way of working, you will solve this shortcoming. I use a smart home use case as an example. It was done within an icon project in collaboration with Ranson, where you have a smart home and we have the knowledge-driven approaches that learn to detect specific faults that we modeled using ontologies, rules, and the knowledge graph. It detects the modeled faults and the derived causes. This is done by using our ontology, the sensor observations, reasoning is done over it, and then faults are detected or the root causes. For example, on the top right corner, you see if a bathroom, if there's a humidity raise in the bathroom, then probably it will be a shower event, so a shower event is thrown. That's purely knowledge-driven reasoning. If there's a humidity increase in a bedroom, that's not possible, so probably there's humid weather and the window is open, so we throw a humid weather event. At the same time, we also implemented anomaly detection models. We used matrix profile in this project, but you could also use autoencoders. It doesn't matter. The anomaly detection, it just detects unknown events, discords, patterns in the data that have not occurred before, and it will create an anomaly for this. Both the output of the anomaly detection and the knowledge-driven approaches are presented in a dashboard where some widgets visualize the status of the home, and in the right bar you see all the events that are detected. When the operator clicks one of these events, an anomaly tab is generated. We use semantic reasoning, so again the knowledge-driven approach, to determine what should be visualized there, and then the operator can analyze the event. If he says, I know what's happening here, he can relabel the event. Instead of an unknown anomaly, he can give it a label, or he can delete it if it was a mistake, a false positive, or he can merge specific anomalies that are related to each other. This feedback is fed back to the machine learning on the one hand and the semantics on the other hand. And it allows to shift from anomaly detection to fault detection. The machine learning model, instead of being unsupervised, can now shift towards supervised solutions and is able to detect events that already have been seen before and that were relabeled by the operator. So here on this slide, you see lots of motives that are or patterns that are discovered. Without the hybrid AI, it would all be unknown anomalies. By thanks to the feedback, only I think he only gave feedback to 2 events. All the orange ones are thrown as faults instead of anomalies. So that's more interesting for the operator, because then an actual label is thrown instead of an unknown anomaly. And when you do the relabeling and you confirm specific events, after a few times, some 5 or something of these events, the semantic rule mining starts processing the confirmed anomalies, so the relabeled anomalies, the semantics observations, so the sensor data that comes with it, and the domain ontology it already knew. And using semantic rule mining, it will learn new rules to detect this event. And for example, here in that use case, we had a showering event. People took a shower. Okay, the semantics knows it's a shower, but if you shower with the door open, there was also humidity increase in the bedroom adjacent to the bathroom. Based to the rules that were defined, we had a shower event in the bathroom, we had a humid weather event in the bedroom, and we had an anomaly detected in the bedroom using the machine learning. Thanks to the feedback, this was relabeled, the anomaly, to an echo shower event, similar for the humid weather that was set as false positive. It's an echo shower, and thanks to this feedback, a new rule was learned that if you have a humid weather anomaly and there's a shower anomaly at the same time or close to each other, then this is a shower echo effect instead of a humid weather. And this way, the knowledge-driven model can be gradually improved and extended. So thanks to this, you can start from scratch without having labels, with limited knowledge models, and in the beginning, your dashboard will show different anomalies and faults, and the more feedback you give, the more concrete events are presented to the operating. So thanks to your feedback, it becomes more interesting, and it stimulates you to give even more feedback. A second approach is hybrid AI to learn partially unknown dynamics, where we have, for example, the slider crank mechanism that is, it occurs in machines like these. We designed our own small version of it. If you have a physical model or you want to build a physical model, you might be aware of Newton's second law of motion, that the forces are mass multiplied with the acceleration. However, there are also friction phenomena you're not able to model, and there's an unknown spring load. Of course, you all know the spring law. It's a commonly known law, but here it was an experiment if the machine learning would be able to learn it. So we don't know these phenomena, we replace them with neural networks, and then we create a hybrid AI model that combines the physics layers with some black box layers, and these are jointly optimized in order to learn what is missing and partially unknown in this model. By doing so, we did the first experiment without a spring, and you see that it learned the friction force and conservative force equal to 0. And if you bring in the spring, then it's the friction force stays the same, but it also identifies this spring law, and it's thus the neural network is able to learn the missing parts in your physical model. So for this use case, hybrid AI can learn partially unknown dynamics in your physical model. A third use case where hybrid AI enables context-aware machine learning, this way outperforming the classical transfer learning I presented in the introduction. Here we designed a methodology. If you, for example, have models for specific contexts, like the compressor in the cold environment and you have it in a hot environment, you have these two models. So you have a trained model for context 1 and a trained model for context 2. And then you have a compressor in a new context. You should learn which model to transfer from, because without that you can do the classical transfer learning, just take a model, do transfer learning. But we improved this by using hybrid AI, by creating a knowledge graph of the specific contexts for each model and of the context where we want to deploy our new compressor in. And then we search for the most similar knowledge graph of our new context with the existing models by doing distance calculations between knowledge graphs. Once we find the most similar knowledge graph, we do transfer learning from that specific model, and we receive the trained model for this new context. You can then just apply transfer learning, but we go to one step further. We identify the differences between the different contexts and especially select data that is able to incrementally train the model and focus on the differences instead of and this way we outperform our research results compared to using classical transfer learning. And then a fourth use case of hybrid AI. Sometimes purely data-driven nor knowledge-driven AI are feasible. And for that, I present the use case of leak localization. Today, you have DMA zones up to 200 kilometers in which they monitor the incoming, the entry with the output. And if the pressure between both is the difference is bigger than what is estimated as the water consumption in that region, they say there's a leak. However, at that time, you need to investigate 200 kilometers of pipes in order to find the leak. That's how it's done today. There's an alternative approach, and that's knowledge-driven leak localization, where hydraulic models are designed based on expert knowledge. However, these models, they have an expensive calibration, and they need to simulate every possible scenario. So they simulate a leak in every position, different size, different positions, and every scenario is simulated, and then they compare what is happening in real life, which scenario fits best, and then they know they find the cause of the leak or the location of the leak. So this scenario simulation, it's really exhaustive and really computational and labor intensive. You could say machine learning solves the job. Then you could do automated localization and much less labor is needed. However, in order to have a purely data-driven approach, one needs to put a huge amount of sensors in the network, where the cost of the water leakage is smaller than the cost of the sensors, and therefore it's economical, not feasible to tackle this in a purely data-driven way. And whenever the network changes, you need to retrain the model. So the only way to tackle this is by using hybrid AI. We designed hybrid AI models that incorporate the GIS data, the topology of the network, with hydraulic models and the hydraulic knowledge that is available into the machine learning. And this way, we need less sensors than using a data-driven approach. We have a lower data cost than purely data-driven. It's more automated than using the knowledge-driven hydraulic modeling, and it has a higher accuracy. Here you see how we did it. We designed the first hybrid model that starts from the topology of the network, the DMA zone we are monitoring. We built a graph that models this GIS topology, And then together with the sensor data that measure the pressure in the network, and so the input stream together with the GIS topology is fed to an autoencoder. It's an autoencoder that is able to embed this graph, so it's a hybrid AI autoencoder, and that one tries to reconstruct the input stream. If the reconstruction succeeds, everything is fine. If it fails, we know there's an anomaly and thus a leak detected. And this way, we, by doing so, we receive a heat map with leak likelihoods. And for this example, you see that the area of the highest likelihood is in the bottom left corner. At the same time, we also designed a hybrid AI model that incorporated physics, hydraulic knowledge into the machine learning. We did this by using the hydraulic tool and do simulations of pressure streams of different leak scenarios that were used to optimize our hybrid AI leak classifier. And then by using the real-time pressure streams, we again get a similar output of likelihoods of a leak in a specific region. And then we brought the two hybrid models together. We had on the one hand the GIS plus the machine learning hybrid AI output, the physics plus machine learning hybrid AI. They are combined in the smart water grid, which is the name of the project, the smart water grid hybrid model. And then instead of using relative relative probabilities, we used the topological spread as an extra heuristic to shift towards absolute probabilities. And by doing so, we reduced the search region of from more than 200 kilometers to about 1 kilometer, and where it took 4 to 5 weeks before to find a leak, now it can be done in several hours. It's only a few minutes for the machine learning, but then somebody has to go there and search the last kilometer. So it's the leak is detected in hours, which is a huge cost gain, and especially saving of drinking water. So I hope I showed that hybrid AI, which combines knowledge-driven and data-driven analytics, it has a lot of opportunities for prognostics and health management, and Peter will show the potential of hybrid AI for control. Here are my contact info if you want to contact me, but I'm here for the rest of the day. So I give the floor to Peter.
Thank you. Thank you, Tom, for the introduction of myself. Thank you, Sofie, for the nice introduction of the topic of today. What I'm going to talk about today is control. And I'm going to take one step back. Yeah? Okay, yeah. I will allow you, Sabine. You can always interrupt me, no problem. Okay, so this will add some extra complexity for me because, everybody had to listen to you because they could not see anything, Sofie. Now I have to try to be interesting as well. Let's see. I want to talk about control. I'm Peter. I'm from the University of Antwerp, also IDLab in Antwerp. We have a team working on wireless technology on the one side and other teams on AI. Of course, this talk will be part of our AI research. And in that AI research, we have a team that works on AI applications. And what you will see is this will fit exactly there. And this will be very close to what we do with industry. But let's first take a step back, because we're talking about modeling, we're talking about control. Why do we need those models? And I'm going to start with a buzzword that everybody hates right now, I think. I'm going to talk about a digital twin. It's used for everything except for what it is really needed, I think. It's used for sales and so on. But what is it for me? For me, it is a digital representation of a real object, but with a specific purpose, and that purpose is that we should be able to do simulations with those models. And can do simulations, we can learn from it, and we can start learning how to control things. But of course, there are more things to use this kind of models. They use it for design, for building, for operation. But for me, the operation, the control is the most important thing. But what is a digital twin when you look at it? It's kind of an old technology. Look at this picture. You see a human being doing something with a machine. I'm not really sure what it does. In a specific, tough environment, I think. And when you look at the model of what you see here is, you have actually 3 models. You have an environment model, the water, which is very specific in this case. You have a model of the machine. That's what we call a plant model. And then, of course, we have the human being here doing the control, and that's what we call a control model. And those things are important when we talk about digital twins. When we talk about digital twins, we focus on a plant model and an environment model on which we want to build a control model. And then if I show you this, you see some very old pictures about some space stuff, and then you think, this is old technology, because they used models to design, when they started creating space shuttles, they used it to build the rockets, and they use it for model predictive control and so on in real systems. So it's all technology. It's there for a long period. But what is different right now, and that's what we all know, there are new technologies involved. We have better AI models. We have those hybrid AI models, which are very relevant to take decisions. We have, of course, better computers, high performance computing, and last but not least, we have IoT. We can connect those models in real time to these actual objects. So we can create an interaction between those models and the object that we want to control. Some people would call it the metaverse somehow, but let's call it just a digital twin right now. Where are we? We want to operate. And when I talk operation, I quite often rely on this picture. It simplifies the entire thing a bit, but let's see, we have that cube. Let's call it a dice right now. We can have some representation inside the model of that, and what we want to do is we want to operate it optimally. We want to roll the dice. How does that work? When we have a model in a computer, we can start manipulating that object in the computer and see what happens, and then based on that, try to go to an optimal controlling behavior. Think back to the dice. What do you do, or what did you do when you were small? Because you're not doing it anymore, of course, because you don't want to cheat. You take the dice, you see where the 6 is, and then you manipulate it a bit in your head, because you are thinking about, if I roll it at this speed, probably it will get to the 6. That's what we are doing. We have a representation of that dice. We try to think what would be the optimal control algorithm. We see things happening with the sensors. We actuate it with our hand, and it works like that. Of course, there are a lot of problems, a lot of things we need to research to make this happen. Because in the early days, we had traditional model predictive control, but in this new situation, when we want to do this in really complex systems, there are some important things that we need to tackle. The non-linearity, the dynamics, the limited observations we have, and the accuracy of the models. We need to tackle that. And we need to tackle that to use those machine learning things to control. Let's look at this picture again, and let's go into more detail about each step that we need to address at that moment. And first of all, when you talk about machine learning, we need data. And when we need data, it comes from sensors somehow. And then, of course, then the question is, what is the quality of that sensor information? That's the first thing we need to tackle. How do we tackle that? How do we internally tackle that? We do not only see to what the quality is, we don't identify only the quality, but we are looking into those models and see what the propagation of the lack of quality in those models will be. Or turn it around, when you are in a certain environment, you want to do control within specific boundaries, we track back on what loss of information we can have throughout the different models based on what we need in the end. Secondly, another thing that is really important in perception is we need more information than just the local information. So if you have like a robot walking, he is next to the house, he does not see that truck. What you want in this is that you have a global perception of your environment. So we also need to combine the information we see from different distributed sensors. So we need some kind of distributed sensor fusion, which is very complex. And we are working on that in different projects. First project you see here is an icon project, SSAFE, where we actually share sensor information between different chips. Seems pretty easy to do, but it's not that easy because there are a lot of privacy issues there. Not all ships, let's say you see Dhaene here, they don't want to share with the null and vice versa. There is specific information that they want to share, that they don't want to share. They're on the sea, they have different kind of qualities, but in the end, what we need to do is give you a global perception of the environment as good as possible to make the shippers move their ships as good as possible. Second thing that we have there is the 5G blueprint project. What we do there is we actually try to automate the driving of trucks. What is the project about? It's about remote driving trucks, which means actually you don't need any AI, you would say. But when you look at it, when you remotely want to drive trucks, you need to use 4G, 5G connections. Sometimes connections get lost. What we do here is we try to fuse all sensor information at a local environment to fill those gaps. When connection drops, we want those things to operate as good as possible. Worst case, we stop, but what we try to achieve here is that they can continue their trajectory, that there are no strange behaviors. Second thing that we want to tackle, and then we come very close to what Sofie was talking about, is closing that reality gap. Because when we work with domain-specific knowledge, we work with the models of the physics models. I'll do my best. We work with physics models, but what we see is, for example, here in a chemical installation, when you use just a white box model, it never exactly resembles what is happening in those specific installations. For this, what could we use? Sofie also told you we could start using black box models. Problem with those very complex chemical systems is that if you want to do that, you need a lot of data. I quite often say, then you build an installation, you want to control it, and when you have enough data to control it, then yeah, the installation is gone because yeah, it was used too many times. So what we do here is hybrid modeling. We use those white box models, those physics models, and we start building either layers on top of that, or we start using all the information there to build a black box model again and train it further on with the sensor information we have. Why is that so important for control? And I'm going to show that here is when we look at controlling another system here, an HVAC installation, for example, what we use to control it is feedback from the users. When it's HVAC, you get feedback on what are the moments or how much time do you exceed the temperature that a certain person what a certain person feels in a specific room, when is it too low, the temperature, and so on. So you have some kind of reward functions. You can build reward functions, the things you use in reinforcement learning as well, to start building the right model there. But of course, there is not enough information because, as I told you, when we would start controlling a building, then probably the building was gone, too old when we have enough data. So we built those hybrid models based on that. We have the physics models. On top of that, we put some sensor information. And why are those models so important? Because we want to create control policies using reinforcement learning on top of those hybrid models. And yeah, it's pretty obvious that the control model can only be as good as the model that we created with that hybrid technology. And here we have, some very specific projects that are going on. Go back, and the movie doesn't start on the left. But we have two very cool projects here on the left. I will elaborate a bit more later on it. We do autonomous shipping. We really put ships on the water using reinforcement learning to control them. On the right side, you see again that chemical installation. We really control chemical installations. That's not true. We don't control them, but we give the operators the information they need to optimally control it. And as I will show later, we have very good results there. Then, of course, very important, there is a safety issue as well. If you want to deploy something in the real world, then you always need to know what is happening. Hybrid modeling is very important there, because when you can add some domain-specific information connected to your objects, you know why those things are happening. What you don't want to have is that a robot starts to have some Terminator behavior and starts to conquer the world. It's not going to happen. Certainly not, but things can go wrong. It's still an optimization algorithm, so if it optimizes in a wrong direction and we don't know why, it is dangerous. And in that sense, we are focusing on using different techniques there. We look at what is the relevance of specific features. We use causality there. We also use surrogate modeling. Tom, we should talk about that. Very interesting, where you can use alternative models next to your own model and see whether the things they see are more or less equal. And yeah, we also start analyzing the models, seeing where the spikes in the network are occurring at certain moments in time. Then another challenge is scalability. Of course, when you want to control such a thing, yeah, it needs to be scalable. We do two things there. First of all, we use different kind of simulation methodologies which we dynamically combine. Here you see a traffic simulation where we simulate at specific areas where we need to have more information at an agent level. Each car is an agent. When we go a bit further away from that specific area, we can start simulating at street level, and on top of that, then we can start building AI algorithms. And a step further, of course, is we use multi-agent reinforcement learning, where we don't control on one specific place, but we start controlling a system at different places, and what we want to create there is an emergent behavior based on what the different agents were doing. Then the question is, how real is this? Give you some examples, one in ports, one in construction, one in processes, and one in networks. In the port, I already told you, and I don't know whether we can start this move. Yeah, it moves. We are really controlling ships, so what it does is it creates, based on perception algorithms, an environment, the local environment, and then on top of that, we start using or retrain the reinforcement learning agent to locally avoid objects and to globally go towards the final destination. A second thing that looks a bit less appealing but is equally cool in my opinion is we see a chemical installation here. It's a reactor where we put some material in. There is a reaction in that reactor, and it gets some other kind of substance out. What you see here is the yellow one is the original strategy that the operator does. The blue one is the reinforcement learning strategy. On the bottom right, you see what the amount of chemical substance is in that reactor, and when it's constant, that's a good thing. Remember that. Above that, you see the temperature we do there. You see a different strategy between the operator and what our agent did. Then on the top left, you see the amount of substance that is put into the reactor, and on the bottom left, you see the evolution of amount of substance that's still needed to be changed into that other substance. What you see here, and that's the most important thing on the bottom left, the process of our reinforcement learning agent stops at time step 600. The other process stops at 800. So we had a 20% reduction of the time that the reaction took. It's cool in simulation, of course, but we really did it. We went to Johnson & Johnson, we asked an operator to do this. We did not get that 20%, we did get 10%. Main reason because their pumps were not able to put that much of the substance in the reactor as fast as we wanted. But even when you have very good operators, you can achieve better things by using artificial intelligence. And that's important to know. And of course, domain knowledge is important, but we can go a step further when we combine those things. This one is less important, but we achieved equal goals in HVAC installations. It's a building at the campus at the university where we are using alternative strategies to control the heating system. Why is that important? And not many people know that, but typically what you have in new buildings is you have central production of heat, and then you have local extra production. If you can get that central production as high as possible, because that's an optimal producer, then and you can reduce the local production as low as possible, then you have an optimal behavior. But of course, that strongly depends on the users of that building, because you have your heating on the one side, but you also have the production of the water for washing your hands and so on, and that makes it more difficult. And then a last example I want to show is we also use this in network traffic, and network we really mean the 5G network traffic, where we optimize the way we communicate in those different layers in 5G to make sure that, for example, here in a drone project, all information goes to that specific drone at all moments in time. Yeah, we work together with a lot of companies. It's just a small part of them. And if you have any questions, these are my credentials. Feel free to contact me, or feel free to ask questions now, if that is still allowed, of course.
Thank you, Peter and Sofie. Maybe I have one question for you. What is the key difference between model predictive control and the control strategy that you presented here?
That's a very good question. I know where the question comes from, because you are also in that domain. When you talk about model predictive control, what we do is we take a simulation model and we do an optimization algorithm on top of that. That's not what we do in our research. We use reinforcement learning, and the reinforcement learner, what it does is, we don't know up front what it's going to do, but we let it play in that environment with certain objectives. And every step it learns, and hopefully in the end, it will end up with an optimal solution. So not a big design space where we have some optimization algorithms or a genetic algorithm. No, we use reinforcement learning on top of that to achieve the goal.
So thank you. We will have to move on to the next session. I would like to thank Peter and Sofie once more. So thank you.
My name is Chris Develder. I'm a professor here in Ghent at Ghent University. And I'll be chairing the session on NLP. We have two speakers for you today. The first is Professor Veronique Hoste, also affiliated with Ghent University. She's heading the LT3 research group, so that's language and translation technology. And she's mainly been focusing on emotion and sentiment analysis, and that's also the topic of her talk today. So I'll give the floor to Veronique.
Okay, merci. Just have a look. Okay, so good morning. So the topic of my the topic of my talk today will be towards more empathic conversational agents. So the focus will be on the two words. So there are no empathic conversational agents yet. So I also want to don't be too eager on finding some solutions for empathic conversational agents at the moment, so I won't give you any. But I will show what we have done in order to reach this goal of empathic conversational agents, and I think we already go a long way into this direction of empathy in chatbots, or also maybe in speaking and hearing conversational agents. So the work I will be presenting is part of the Flanders AI program at one hand side, and at the other hand side is part of an FWO project we have currently. And this general goal of emotions in human agent conversations is in fact very old. So here you already have a statement of Picard in 1997, and in AI terms 1997 is very, very old. And he states that if we want computers to be genuinely intelligent, to adapt to us, to interact with us, then they will need the ability to recognize and express emotions, to have emotions, and to have what has come to be called emotional intelligence. So in fact, if we talk about artificial intelligence, no artificial intelligence without really understanding language. And language is not only understanding the factuality about language, it's also understanding the empathy involved in expressing language. Okay. So when we think about emotions in human-agent conversations, I think the two statements I put there are in fact a bit kicking in open doors. So research on human-human interactions has shown that empathic engagement has a positive effect on the outcome of several communication tasks, such as, for example, persuading voters, patient satisfaction and compliance, and we also see this in a CRM context. So in customer relationship management, we see that if you react correctly to a customer complaint, and if you react empathically, well, it reduces churn and increases customer satisfaction. We all know this. We as human beings often know how to do this, being empathically in our conversation with customers, but how do we learn chatbots, or how do we learn conversational agents to also understand emotion and act upon it? So when we look at emotions in human-agent conversations, quite some work has already been done in the past, but focus has mainly been on, from the domain of affective computing and also in social robotics. So for example, here also in our university. And until now, the focus has mainly been on visual and paralinguistic characteristics. So on visual characteristics, I'll talk about Ekman in some minutes, and also paralinguistics, so the signals you often find in speech, for example, pitch. Yeah, but at the moment there's very little being done on trying to understand emotions in text. And this is in fact what we need when we are, for example, in a chatbot setting. So there we need fine-grained emotion detection in text. And when we try to model conversations in chatbot contexts, well, people often for example, in a CRM context, start off angry, and hopefully, depending on the responses of the chatbot or of the human operator, in the end, they turn well, happy might be a bit too much, but they are satisfied with the solution brought forward. So you should be able to model dynamic emotion trajectories, so how emotions evolve in time, and what response strategies work well, what response strategies are maybe counterproductive, and in the end, you just want to have a happy customer. So the focus of my talk today will not so much be on the left side of the slide. So I won't talk about the ASR part, about the TTS part. I will mainly focus on the natural language understanding part, and maybe also briefly talk about the natural language generation part, because one goal is not only to understand emotions in text. The second, at a given point, you should also be able to convert this knowledge into an empathic answer to your customer. Okay, I think by everybody in this room knows what sentiment analysis is. It's already a fairly old application being used a lot in business contexts nowadays. I think most companies in Belgium, but also public governments use sentiment analysis to know what their stakeholders think of them, and often it boils down to simple polarity labels, so positive, negative, and neutral. So in fact, it's mood detection. So can we determine the mood of a certain person towards a certain company, towards a certain product? So what we have been doing in the team for the last years is that we try to surpass this more coarse-grained sentiment level to a more fine-grained emotion analysis. And there's quite some work to do, because when you look at sentiment detection, so polarity classification, it's only scratching the surface of what is really said and of what is really interesting from a stakeholder management point of view. So what is important, also implicit sentiment. So most of the current tools on the market don't model any implicit sentiment. They model explicit sentiment. So they model explicit realizations of awesome, great, so mostly explicit sentiment in social media. So what we have been doing in the last years is is also focusing on implicit sentiment, for example, in the framework of economic news detection. So you have economic articles being written. I think that you all know by now that, not being an expert in economics, that the stock markets don't behave rationally. So they behave on the basis of what is being written in news often. And so the reaction there's a reaction to positive news, there's a reaction to negative news. And this trying to, or being able to model this sentiment, these events, and the sentiment attached to these events, and being able to model this would be very interesting, not only for portfolio management, for example, but also, for example, in algorithmic trading systems, which currently mostly work on the basis of, financial data at the moment. So what you see there, some months ago, 2 months ago, a research, a PhD was defended on this topic on economic news event detection and sentiment analysis. And you see on the bottom of the slide, you can see how we annotate these data. So it also led to a gigantic database of annotated data with not only implicit sentiment, but also with events. And why are these annotations important? Sofie already talked about it. Data is crucial when you want to develop good machine learning algorithms. And in our team, we develop a lot of data sets. Yeah, because we know that if we don't have good data at our hands, we will never be able to develop sensible systems. Okay, another thing which is important when we think about sentiment is irony. You know that when we express sentiment, we often do this in a very creative way, and often we use irony to express that we mostly are not happy. And this is also something we've worked on for quite a while now, and which is important when you want this empathy in your chatbot. And what is important or interesting there is that it's not only about sentiment analysis, it's also about common sense knowledge modeling, yeah? And it's not about common sense knowledge in building common sense knowledge bases with factual knowledge. It's in fact common sense knowledge, it's connotational common sense knowledge. Things happen in life, and some things we like and other things we don't like. But how do we try to model this? And you really have to have this dynamic modeling of this common sense in order to be able to model any irony. Because as you see it here in this slide, you find irony is realized through a clash between sentiment and something which people usually don't like. But how do we know what people usually don't like? Yeah. So this is also one of the research lines in our team. And if time permits, I will also talk how we try to tackle this. Another important fact is if we want to know, if we want to build empathic chatbots, we don't only want to know whether they are positive, negative, or neutral, or whether the customer is positive, negative, or neutral. We want to know what this customer is positive, negative, or neutral about. And mostly we are interested in knowing what he is negative about. So in fact, we need aspect-based sentiment analysis. And this is a slide referring to a current TETRA project we have with a couple of companies, of which I see some in the audience. And this is a TETRA project on aspect-based sentiment analysis and emotion detection. And what is the goal there? The goal is, first of all, to detect what people are talking about, and to try to categorize it, and also to link emotions and sentiment to it. And also there, this is also very domain dependent. The idea is also to, when the system makes errors, to have some kind of feedback loop in order for the machine learning system just to retrain on a specific domain. And then the last part I would like to talk about is how can we have emotional systems? So emotion is not about positive, negative, or neutral. It's about finding out whether people are really angry, whether they are annoyed, whether they just want, whether they are disgusted, and so on and so forth. Because these are the people you want to directly respond to, for example, when we think about CRM context, or when we think about a chatbot in, for example, we worked together some years ago with a suicide prevention center, in which we developed a system for the detection of suicidal thoughts on social media. Well, there the emotions are completely different. So there you want to feel, you want to be able to directly find these suicidal emotions, these depressive emotions. Okay, so this again is then for example, here I also again refer to our project on emotion analysis and our Vlaio project. So all these emotions are again fed into a system that is mainly using machine learning to do the processing of new unseen data. Yeah. I didn't talk about methodology. I think in the first talk this morning there was already a very good overview of feature-based machine learning approaches, neural network machine learning approaches. We use them all. So we both use feature-based machine learning approaches if we don't have enough data at our hands. We use BERT-based, transformer-based approaches, which we fine-tune on our data sets if possible. And we try to see what works best in which specific setting, which is in fact completely normal in any scientific context, I think. Okay, so I think I mainly explained this to you, but a brief note on data. One of the huge problems we have, for example, if we want to build empathic chatbots, is that we don't have data. It's easy to build systems if we have data, but we just don't have any. We have data for emotions, which we mainly build ourselves. We have data for all the other stuff I talked about, but this is what we are currently working on. So at the moment, we are just making our hands very dirty by hiring a large bunch of job students to do annotation work for us. Yeah, well, my hands are not that dirty. And okay, so, and what are we doing at the level of data construction? So we construct personality data. How do we do this? Also in citizen science projects. So we try to define citizen science projects, such as, for example, the Burgerpraat project, in which we try to collect data from 1,000 Flemish citizens, personality data, but also spoken data from them, in which they talk subjectively on all topics they like. So we want them to express emotions in text. What are we also doing? Crawling a lot of data, try to find data, all data we can lay our hands on, and then we have our battery of job students that do the annotation work. And what we also do now in the context of chatbots is Wizard of Oz experiments. So this has to pass in an ethical committee, because in fact we fool our participants. The problem in human resource conversations is that when the customer starts being very angry, he's taken offline. Yeah. Then we don't have interesting data anymore. So what we now did is set up experiments, Wizard of Oz experiments, where we had different scenarios and where we try to evoke different emotions in the participants. The participants think that they are talking to a chatbot, but in fact one of our job students is playing the chatbot and is trying to make this person behind the computer angry. And the strange thing is that I think 98% of the participants didn't realize that they were talking to a human being, while at a certain point this chatbot was really rude. But it gave us fantastic data, and now we are starting to work on this data to build our empathic chatbot. Okay, so I hope I explained to you what we've done on in the domain of emotion detection and how far we got. I think we got quite far on the text level, but now we have to integrate it in a conversational setting, and we are currently working on data collection to mimic this conversation setting too. Thank you very much.
Okay. Yeah, we can maybe take just one question, real quick. Okay, so just for the audience, the question is about how do you distinguish between cultural differences and how do you accommodate that, basically?
Yeah, I think this is a very interesting question, and we are currently also looking into this question. So at the moment, we mainly focused on emotions which are well, in cultures, so for example, in English, in Dutch, in German, in French. So in fact, we can consider them culturally very close together. But at the moment, we are also doing experiments on the portability of our systems to, for example, do emotion detection in Hindi or do emotion detection in Chinese, and to see whether we are able to find, and we combine this with language detection, whether we are able to find language agnostic or culturally independent features to build, in fact, a culturally independent emotion detection system. Yeah, that's work we are currently working on.
Thank you for the interesting question. In the interest of time, I propose that we leave further questions until the end of the session, if time's left. So let's now move on to the second speaker. So that's Jens Nevens. He's a PhD student at VUB, so Brussels University. And he works mostly on how to learn or to teach intelligent agents, or how to see how they can represent and learn linguistic structures. And then use those learned structures in advanced perception, reasoning, and also communication tasks, so also in the context of chatbots. So I'll give the floor to Jens and give him some time to connect his laptop, because he also intends to give a demo, actually.
Thank you, Chris, for the introduction. Hello, everyone. So I'm Jens. I will talk today about hybrid procedural semantics for conversational agents. But before I explain to you what hybrid procedural semantics are, I have to give credit where credit is due. This is not my work that I will present today, but it's the work by Lara Verheijen, who is doing her PhD on this topic, supervised by Dr. Paul van Eecke and Dr. Katrien Bults, who could not be here today. So I will try my best and explain their work as good as possible. This work, Lara's PhD, is situated within the AI Flanders research program within Grant Challenge 4, Human-like AI, in Work Package 2 about conversational agents. So I would like to start this presentation by trying to formulate for us what is the main challenge in conversational agents. And for us, this is the integration of new observations that come in, for example, text in a chatbot or images, and integrating this with previously acquired knowledge. So knowledge that is built up over the course of the conversation, but this can also be other knowledge, like domain knowledge that it's necessary for your particular application, or ontological knowledge, common sense knowledge, and so on. Closely related to this, and I put this between parentheses, is the integration of unstructured data and structured data. So these texts and these images, this is completely unstructured, and we want to analyze this, extract all the meaningful information that we need, structure this, and store this. This can be in any way that you want. This can be a table, this can be a knowledge graph, an ontology, a database, and so on. So when is a conversational agent considered to be good or successful? We think you have a good conversational agent when it is able to combine both of these sources of information, so new observation and previous knowledge, because it is only then that it will be able to have a meaningful and coherent conversation with end users. So this is a big challenge. And our first step in tackling this challenge was a case study on the task of visual dialogue. So this task is illustrated by the figure that you see here. And the task is to answer a series of questions about this image. And to successfully do this, you need to integrate information from the question, the image, and the dialogue history. So we can see this when looking at the example at the top of the slide. The first question about this image is, are there any triangles? Well, to answer this question, you only need information that's available in the image. But then the second question, how many? Well, here you need to refer back to the dialogue history. How many what? You need to go back to the previous question, and there you will find they were talking about triangles. So then you combine this information with the information that's in the image to find the answer that there is only one triangle. There are other problems to solve as well, like solving coreferences. This is illustrated in the third question. Is there an object to its left? Well, what does it refer to? Again, we need to access the dialogue history, and we need to access the image and combine this information in order to provide an answer. And we applied our methodology on two benchmark datasets, the MNIST dialogue dataset and the Clever dialogue dataset. So what is our approach that we used on these datasets? It consists of 3 parts. First, we have computational construction grammar. So this is our language component of the system. Then we have hybrid procedural semantics. And the third component is a conversation memory. So I will explain these 3 components and how they fit together. And in the end, I will give a live demonstration of our system applied to this Clever dialogue dataset. So the first component, computational construction grammar, this is the language component of our approach. And specifically, we use fluid construction grammar, or FCG. This is software that we develop in the AI lab in Brussels. And what can you do with FCG? You can map a linguistic utterance onto a representation of its meaning. This we call comprehension. And you can also do the inverse process, so mapping a meaning onto a linguistic utterance, and this is formulation. So it's a bidirectional system. Why? Because we also use it in research on the emergence and evolution of language, and there we want our agents to have bidirectional language processing capabilities, well, like we do. In visual dialogue, only the comprehension aspect is important. And what's also important is that FCG offers us a transparent and human interpretable linguistic analysis. So this is a search process that's going on, and every step of this process you can investigate why FCG found that particular linguistic analysis of the question. The second component of our methodology is hybrid procedural semantics. So in order to explain this, I will first explain what is procedural semantics. This is a way to represent meaning such that it is at the same time a representation of the meaning of an utterance, but also an executable program. How do we do this? This meaning representation is structured as a network, and the elements in this network we call primitive operations. And the links in this network, these will determine how these primitive operations share their information. And if we execute this network, if we execute this meaning representation, because it is a program, we get the answer to the question. Importantly, the layout of this network is determined by the question. So how does this fit together with fluid construction grammar? We analyze the question, and fluid construction grammar gives a representation of its meaning, and this is exactly this network structure. This is a network of primitive operations that we can then execute. So now you may wonder, what makes it hybrid? Well, in order to execute this meaning representation, we need to implement these primitive operations. And you can implement them in any way that you want. So what we did was combine subsymbolic primitive operations that do pattern recognition on unstructured data. So basically what this means is we have primitive operations that behind the scenes call neural networks that operate over the images. And we combine these with symbolic primitive operations that do higher level reasoning on structured data. So what does this mean? We have primitive operations that can do set operations, logical operations, search with heuristics, unification, all kinds of symbolic operations. And they operate over structured data, and this will be the conversation memory that I will introduce in the following slides. But with our hybrid approach, we have the best of both worlds. We know that these subsymbolic operations are really good at pattern recognition. We know that these symbolic operations are really good at reasoning. And with this approach, we can combine them in a very flexible way in this network, depending on the linguistic analysis of the question. So the third component is the conversation memory. And in this task of visual dialogue, every turn in the dialogue conveys new information. New information about the scene or about the image becomes present after every turn in the dialogue. And we use a conversation memory to keep track of what has been said in the dialogue. And we store this as structured information in a human readable format, so that after every turn, you can see what the agent has understood, you can see what it knows about the scene, what information it uses for reasoning, and so on. And our symbolic primitives that are part of the meaning representation, these can access the conversation memory in order to use this information to answer a question, and they can dynamically expand the conversation memory, so that if new information becomes available, it is also incorporated in the conversation memory. So here I provide an overview of the system with all three components that I have discussed. So on the left side, we start with the question. This is analyzed using fluid construction grammar, where we get a meaning representation, but a procedural semantics representation, so an executable program. And then we use a hybrid execution mechanism to execute this network in order to get the answer. And our hybrid execution method consists of primitive operations. Some are symbolic and access the conversation memory. Others are subsymbolic and they use neural modules to access the images and attentions and so on. So before I give you a demonstration of the system, I have here a summary. So at the start, we formulated the main challenge of conversational agents as combining or the combination of these unstructured and new observations with structured knowledge. In the visual dialogue task, we tackle this by introducing a conversation memory that explicitly captures and dynamically expands this knowledge. In this case, the knowledge is the dialogue history. And we introduce the concept of hybrid procedural semantics that can combine in a very flexible way the strengths of both symbolic techniques and subsymbolic techniques. And finally, something that we also think is very important is that the entire reasoning process in our conversational agent is transparent and human interpretable. So at every step, you can inspect what the agent knows, you can look into its brain, and you can see what decisions were made on the basis of what data. So to finish off, I will show you a demonstration of this. Wait, I will have to check. Sorry, I will quickly try to mirror the screens because otherwise. So this is our demonstration that we made. So this was also made by Lara and Jeroen, who worked as a developer at the lab. And in this demonstration, we built a chatbot-like interface that interacts with our conversational agent on this clever dialogue task. And you can find this demonstration also online on our website of the AI group within the AI lab, so you can try it out yourself, well, later. So at the start, you have to choose an image that you want to talk about. So let's say I pick here this second image. And every dialogue in this clever dialogue task, it starts with an observation. And here the observation was made, there is a purple object. Okay, we continue. And then on the left side, as indicated, you can look inside the brain of the conversational agent. And it consists of 3 parts. So at the top, you have the observation. There is a purple object. And then in the middle, there is the execution network that is shown. But let me quickly switch this. So this, what you see now, is the result of computational construction grammar or fluid construction grammar. It has analyzed this observation. There is a purple object, and mapped this onto a meaning representation in the form of a network of primitive operations. And this network is what you see here. So these are the primitive operations that the agent needs to execute in order to compute the answer or the topic of this observation. And if we switch back here, then we can see all the intermediate outputs that were computed by the agent. So you see, it starts with the image, then we analyze the image to get the objects. We filter the objects for purple objects, because this is stated in the observation. We check if there is a unique object, and we check if there are any objects left, if the set of objects exists. So you see, we use a combination of symbolic and sub-symbolic operations. So here, this exists is just a set operation, is the set not empty. But even our sub-symbolic operations, they are completely transparent, because we use attention-based neural networks all the way. So at every step, you can see what's going on. And then at the bottom, we have the conversation memory. So this will store the information of the dialogue in a structured and human interpretable way. And what you see here after this first observation, that it knows, okay, there is an object, we call it here object 5, and we know about this object that it is purple. But at the moment, this is everything that we know. So I will just show you one more example so you can see how the conversation memory expands. Because after the observation, you can ask a number of questions in this task. So let's pick this first question. What is its shape? So this is a co-reference that we need to solve. And again, it consists of the same steps. We start with the question. With computational construction grammar or with FCG, we analyze this question and map it onto a meaning representation that is shown here. And then we use our hybrid execution of this meaning representation, that you can see here. So here we get the image, but also with a symbolic operation, we get the conversation memory that was built up in the previous turn, and we get the last topic from this conversation memory. Why? Because we have here this co-reference it. So we need to find what this it is about. And it is the topic of the last turn. So we find it here, and then we combine this image with the symbolic information to find the last topic in the context. This is shown here, it's this purple cube, and again, we check if it's unique and we query the shape. And in the end, with this answer computed, we can expand our conversation memory. So now we still have only information about a single object, but we know now that it's purple and it's a cube. And like this you can go on and on, but in the interest of time, I will end it here. So thank you very much for your attention.
Okay, thank you, Jens. Maybe a quick question from my side. So you illustrate this particular application which deals with visuals of objects, but can you comment on what sort of knowledge you need to program in there, or how do you enter the knowledge that we're talking about cubes, spheres, and so on and so forth? Yeah. Or put it differently, if we move to another application where we're discussing animals and who's chasing who, what do you need to change, or what kind of sort of programming or information do you have to enter into the system, and how do you do that?
Yeah. So there are several pieces of information that you do need, of course. So first is the linguistic analysis. You need a grammar to transform these questions into these semantic or meaning representations. In this project, this grammar is engineered by Lara, but currently we also have several projects running where you have where you can automatically learn large coverage grammars from annotated data, or you can learn grammars from interactions with the environment, like a situated agent or a robot that interacts with the environment and with other robots, and this way learns a grammar like this. Then you need to design the primitive operations themselves and the concepts that can be used in them. In our group, we also investigate a lot how these concepts can be learned from interactions with the world. And these primitive operations, these are usually defined on beforehand and typically domain specific, so they can optimize. We can optimize them for the particular domain in which we want to use them.
Okay, thank you. Is there any final question maybe from the audience? If not, you will also have the opportunity, I think, to talk to both of the speakers during lunch, which is due about now, I guess, or not? One more session, okay. Okay. Then we'll cut here and then let you move on to the next session. Okay, thank you. Thanks for attending. Bye-bye.
Hello. Yes. So good afternoon, everyone, to this session on automating your AI. And today we'll dive into 3 topics: data wrangling, feature extracting, and MLOPS. I'll leave the discussion of those topics to the speakers, and we have 4 speakers and 3 presentations. But first off, we have Ilkka Kosunen, who originally got his PhD from the University of Helsinki. And he worked mainly on analyzing psychophysiological signals using AI and machine learning. And today he works for IMEC, and he will present some work on productionalizing your data wrangling and feature engineering solutions using MLOPS. And also he will say something about the feature store, which is quite an interesting concept, but again, I'll leave that to him.
Yeah, thank you. So I had an introduction slide, but you introduced me already. I just quickly say that the topic of MLOPS is very complex. I can hardly scratch it, so please contact me afterwards if any of these pieces feel interesting. So first, why MLOPS? And then I tell you what it is. One thing I want to say that the MLOPS that I'm talking about came like organically. It came from my own needs, that I ran into problems and then I needed to have a solution. Unlike many other things that come from like a top-down, that you should do this. I did these things because I had no other way. So first, why MLOPS? So any of you who have been in any kind of real data setting probably recognize these things. So pre-processing of data is done in some random scripts written in all kinds of things from shell scripts to anything. Exploring data analysis all over the place in Jupyter notebooks and nobody keeps tracks of it. And maybe somebody puts it in the GitHub, but that's not always. Data can be in all kinds of formats. There are CSV files and some binary files, and they are sent in email and FTP servers. And pipelines are usually always totally manual. There are no so-called DevOps pipes on any of this stuff. If some part of the pipeline needs to be rerun, then the whole pipeline needs to be rerun. There is no centralized way for the management, for example, to see what's our performance on different tasks, so on and on and on. There is like a lot of problems from going just the basic Jupyter notebook in the laptop into an organization that can actually use these machine learning models that are trained. And that's what I'm talking about. So by using this MLOP paradigm and the tools, I hope that all the experiments and studies that are run are fully replicable and reproducible. And tracked and documented for governments and other purposes like that, so GDPR and these topics. So for example, I can go back now 6 months and see exactly what model I run, at what time, what was the git commit, what were the parameters, what were the environment, everything. And then there are even more complicated topics like once you start to deploy these models online, you have to take into account things like data drift. So as a very concrete example, now that the pandemic hit, all the models that were trained on any kind of behavioral data went all nuts, not because the models were bad, but the behavior of everybody changed, and so everything had to be retrained. And this can be really difficult unless you have a good system for all of this. So basically I'm talking about tools to make everything like developing models and algorithms and monitoring them and making everything like testable and tracked. So what does this mean? So this is a famous picture from a Google paper that shows that the Jupyter Notebook machine learning model is this small black box surrounded by all the rest of the stuff. And MLOPS is all the rest of the stuff. As a background to everything, when you start to use a cloud service, almost always you have this kind of a layered structure of data. So you have one lake, usually called bronze, where you put all the raw data as a read-only place. And then you take kind of features out of that to the silver lake that can be then used to train machine learning models. And the feature store that I'm talking about is going to be a fancy way to do the silver part, and machine learning ops in general takes the whole 3 buckets. So what is MLOps? First of all, it comes from DevOps, which might be not so familiar. DevOps is maybe 10 years old, which means that there's the continuous development pipelines that when somebody in a software development team pushes something code into GitHub, it's automatically tested, unit tested, syntax tested, and maybe even pushed to production. The MLOps is the same idea, but it contains not just the code, but also the data. And that is actually quite difficult, because if you have an algorithm, like some sorting algorithm, it's kind of a static. It works now and it works forever, but the model doesn't work if the data changes, as in the pandemic example. And the feature store is just more than just a database at the Silver Lake. It actually has all kinds of tools. I don't have time to go to all of them, but for example, you can do the kind of context drift detection on feature level instead of just model level. And this means that the modern machine learning production pipeline has like a 2 DevOps pipeline combined. So first there is the data engineering pipeline, where you, for example, take raw signals like electrocardiography and PPG and create a feature like heart rate. And then on top of that are then the machine learning people who then make some kind of AI from those parts. And these are then separated by the middle part, which is now, in the last couple of years, has been called the feature store. So feature store is a very recent development. I think it came from Uber, that has it as part of their Michelangelo platform. But now most of the big players like Netflix and all have their internal feature stores. But for general public, it's a very, very new topic, and I highly recommend to take a YouTube search for it. It's a very useful thing, but very, very new. And the previous picture actually also reminds me of another problem in data science projects, that there is this concept of data science unicorn, that you just take one person to run this whole thing, and it doesn't work. You need a bunch of experts. You need a data engineer, you need a data scientist, you need a machine learning engineer, you need a DevOps person to be able to do this. But now in many, many places, it's just take the person who has some background in machine learning and make them do this whole thing, and it is not possible. So that's something that should go to everybody, that data science is a badly named term. The fact is that data scientists cannot do data science alone. Data scientist is only like 1/5 of a data science project. Data science project looks something like this with all the pipelines and everything, and it's highly complex. So what, for example, we have currently in IMEC is that we have all kinds of data sources that go to this bronze lake, which is Azure data lake. And then we use these lakes as a kind of interface. So it doesn't matter how I make the features for the machine learning models, it's all the same, they just get the features. So at some point, for example, I have a very complicated model that extracts all the data from one person, and it may be very slow. So what I do then is like I can launch every person into a separate container using the cloud. So my algorithm works like in a constant time. Whether there's one person or 10,000 people, it's just as fast. And MLOPS kind of facilitates these kind of things. So you can do containers, and you can use Spark and everything. And it doesn't matter whether I use Spark or containers or whatever language to make the features in the Silver Lake. Then the machine learning people can build on top of that using, again, a bunch of technologies. So sometimes we use Azure ML service or maybe Databricks. And then comes the whole serving part, which is its own jungle. So currently, MLOPS is so new that there are so many technologies competing with each other that you will get lost. So just pick something that seems to work and go with it. So there are ML flows and cube flows and 10,000 different types of flows. But that's when new technology comes. It's usually like that. Another way of doing this pipeline that you can think about is that data is ingested in the raw data lake. Then there are actually several steps. Usually there's like a data cleaning and filtering, and then actually just the feature engineering, and that goes to feature store, or will go to the feature store. I'm only now adapting. I'm actually testing 3 different feature stores, but it could go on SQL table. So the Silver Lake is like a bunch of different feature representations. But again, the key point is that it doesn't matter how it got to the feature store or the Silver Lake. The top models can use it without having to care about it. How much time do I have? Time. Yes, yeah. Then I kind of run through. So I have a little bit more time. Yeah. So I kind of had to run through a lot of stuff, and I had no way to cover all of this, but the key points here is that there is a lot of new development in how to actually productionize machine learning models. So go from like just doing something on your local laptop to actually having a service that serves million people. It's a very developing field, so don't be scared. But there are also just solid systems by all the major cloud providers. And yeah, that's it. Please come to me afterwards if any of this rings any bells, because I'm more than happy to talk.
Thank you, Ilkka. All right, so next up, I'm very happy to introduce Wannes Meert. And Wannes Meert is the innovation manager for the computer science department in the KU Leuven, and also my direct colleague. And I will leave the presentation and the introduction of his topic to himself.
Okay. Thank you for the introduction. So indeed, I'm Wannes Meert, and I'm an IF manager in the DTI research group at the computer science department at KU Leuven. And I'm going to very briefly introduce how we try to combine learning and reasoning to get a bit more out of your data. Just to give a bit of context, these are all my colleagues and the topics we work on, but I'll not go into details on that. So let me just start with the task I want to discuss today. Probably very familiar to a lot of you. We're given some data, and I'll focus on time series for the session today. And in the end, we want a label, value, or a score, say an anomaly score. And you can see the picture underneath. You're tracking this, and you're trying to predict some things that are happening, like an anomaly that is oncoming and that you want to predict before a critical failure happens, for example. And so the challenges, as we've seen already in many of the previous sessions, we need labels, we need annotations, we need pre-processing, we need knowledge, we need a lot of things to get this thing to work. Now, how do we typically approach this? Most of you, I think, is you have a model that tries to take in the data and try to predict it. And then I want to claim that typically there are just two steps here, if you think about this. And we can look at this in three different ways. Because we need, in one hand, feature extraction. We're never going to do something with the raw data. And on the other hand, we want to learn from this data to predict something, for example. And we can do this, you could say, the good old-fashioned way and just use domain knowledge, signal processing, physics, mathematics, and we just have some attribute value model which we fit to this. We can automate this completely, more the machine learning way, and we do feature construction, where we already would consider things where we automatically try to extract all these features like TS-Fresh or TS-Flex. The next speakers will go into that topic, and AutoML to find our best model. Or we can try to integrate this entire pipeline, and that's more like the deep learning approach, where we try to learn these features while we're also trying to optimize our model. And so all of these things have in common that we need to somehow find more useful or meaningful features than we have in our original data. That's the gist of it. And I'll give a few pointers to tools that we've been working on where we try to achieve this. And maybe to also say which of these is now the best. The problem is it depends. There are tons of papers that always come out, and then this is a very nice one from just a few months ago where they did again an analysis, and in the end it depends. It depends on, do you know what are good features for a certain use case? Do you know your model very well, or don't you know your model very well? So can you tune it in the right direction? And depending on all of these combinations, you typically win or lose this. And so often the simple models perform very well because people know and understand them very well. Okay, and so the challenge that I want to tackle also is that these features can be heterogeneous. This is the top image, is some data from a store, and you can see that during the day it's very stochastic. You don't know what happens in a store, how many customers come in and all these things, but you can compute some summary statistics on that, which is the left bottom image, which we then can use to generate features to kind of describe what is happening. On the other hand, like in the morning, you can see these peaks. Those are actually very predictable shapes. This is a maintenance operation. So for that, we might just want to look at what's happening. And ideally, we want to combine all of these things together. But the question is always, how do we find these things? And so one of the first things that often happens is just time series clustering, which is a very old technique by now, but still highly relevant and still in popular demand, because there's nothing easier than just dumping a bunch of time series, trying to cluster them and find common patterns. And so the first solution in how to solve problems with that, because what you can see in the top left, is that often this doesn't perform very well out of the box. You might not see it very well, but on the second row, you can see that I circled this subtle sine wave. So this is a problem, because actually this should be in the third row, because that's where you have this sine wave. The problem is you never can get this normalized very nicely, so this sine wave is actually closer or smaller than the noise on the signal, if you would accumulate, which most distance measures do. But again, here we can use this first approach and just do better pre-processing with our expert knowledge. In this case, you difference it first, so you use something like differential dynamic time warping or something like that, and suddenly magically your thing works. And this is just using your expert knowledge to fix this. The problem is this requires both domain knowledge and expert knowledge on the machine learning or the distance measures. So the challenge we set to ourselves is, can we try to automate this a little bit? And so the approach we followed here is, can we just have very flexible feedback from the user? Because in this particular case, the previous one, it was easy to ask the labels. There are 4 different behaviors. But often our experts or operators cannot tell us what the class is, whether it's A or B, but they can tell us like this is not the same as that, or this should be in a separate cluster. So if we just start from that, we already have feedback, and we can consider this some kind of labels. The only problem is it's not a class label, and it's not a regression type of thing, it's not a value, so we have to reason over it. We have to indirectly use this knowledge. And that's what we do in semi-supervised learning or constrained clustering and various approaches. And why is this an advantage? What you see on the top is like a very simple case. You have just this upwards time series, and you have this kind of plateau. So the interesting thing is that a lot of time series distance measures, they cannot really easily take them apart, because the left thing you see is actually closer to the plateau. So the left upwards slope is closer to the plateau than it is to the right one that is also upwards. And the simple reason is that at the end it falls down again, and then it's very stable. And depending on how long this part is, it thinks that that's a good match. So we as a human immediately think that the slope is the important thing, but the distance measure looks at everything. But with a little bit of feedback, like just asking the user, do you think this is the same or this is not the same? It kind of clusters this in a 3-way format, and then tries to group them back together based on this feedback of this has to go together or this does not has to go together. And so now with very indirect flexible feedback, we can use this to also find subtle patterns, like there needs to be a little bump, or there needs to be like a little tilt in a signal, by just having a bit more feedback from the user than just trying tons of hyperparameters. And so the idea is that this is now something we can use as a feature. We're just going to look for these shapes that are very representative of what is in our signal and that are typically reoccurring. Now, the other problem is we're looking at just one series. And so this brings me to another tool, which is TS-Fuse, which says, okay, let's just look at combinations of these features. And the interesting thing about this, while it is difficult, because on the right what you see is one example of how we're going to combine this, and then the search space is quite gigantic, so you need to be a bit smart about it, is that it allows us to do combinations which are quite hard to a machine learning tool. And so the simple example here is that you might see that there is a ratio in there, which is just dividing 2 signals, which and this is for sports science, runners, fatigue, injuries, is a very good one to look at. The problem is most machine learning tools or machine learning models, doing a division is not in there. You can do additions, you can do multiplications, say a neural net, but they're never really doing division. Well, division is just here like a magic feature. Once you have that, it's very easy to predict it. So what we're searching is these kind of operations that the machine learning will not directly find maybe, but that we can try to add up front by then again thinking about, is this feature now better for our model or not? So you already see that this look closes a bit more this end-to-end learning that you want to do, but not restricted to what the model can express. I think that's the key message here, and over multiple features. Now, this brings us to the next type of heterogeneous data, because in the end, that's the issue. We have data from multiple sources, and it's never just one nice time series, or it's never just one nice table. So here, this is an example already, where the time series is combined with tons of events. This is from windmill simulations, because both of them are important. Depending on the setting of the windmill, what the operators indicated, you have different time series. So we want to combine this information, and in this case, we'll transform everything, kind of like features, into events, also the time series, and then use that, in this case, to find anomalies in this data. And so I think that brings me again better to the essence that we need to combine more and more data sources, but in a kind of intelligent way. And here what I've proposed is to kind of translate everything into the same format, make everything events or make everything a feature vector. And this sounds nice, but of course this is also not a full solution. And what I think is there, the next step is to move to constraints, because we have now an Excel table. And in this Excel table, there's also tons of information available that might not be directly available to us, but also a lot of time series collected like that. And then people make all kinds of smart formulas in there, or no formulas, they just record it like that. So the tools here, what they try to do is data wrangling. They figure out that there are tables here, they figure out what are rows, columns when they have the same type, but also the formulas that are in there, if there are no formulas. Because often you just get these Excel sheets as kind of like a data format, and not with the kind of computations in there that you would expect. No, we just get the numbers. But if you find these constraints, this can be more than just what's in there intentionally. You can also find patterns, constraints, that a certain row is a linear combination of another, or that it's repeated in another type of table, that there are keys in between them. And in this case, well, you simply find that there is a sum relation and that there's kind of a prediction that you can do, and you can kind of autocomplete these tables. Or if the autocompletion is different from the actual filled-in value, you have anomaly detection. And so you see that the complexity of this reasoning immediately goes up to use more and more kind of like features you extract from these tables. And then the final step, if we bring all of this together, is, and I'll skip that for the sake of time, is to have more contexts. And so the idea here, and we've seen this already a few times in the previous speakers, and I believe this is a good direction. This is part of an Icon AI project that we're doing together with the colleagues of Antwerp and Ceres, is that there is typically not one model that can cover our data very well. And that's something that we need to deal with at the model level. And the simple example here is, again, on the top left, is this kind of time series. If you want to predict that, turns out it's very difficult. It's very hard to get kind of like a pattern in there, until you figure out that there is more knowledge about this, of course. And this is a machine, and a machine you operate, and operators push some buttons. And if you kind of add that, you can segment it trivially. And then it becomes a very predictable model. And turns out you don't need one model, because this depends on what they're making. And then you get different curves. And in the end, these curves, as you can see on the bottom, they're very simple. You didn't, in the end, even need machine learning. This is just fitting, because it's such a simple physical model. The core was to figure out, and that we did by learning, that there are different contexts. And if you're making machine weld one thing and then the other thing, you get different temperatures and all these things. So the key ideas here, one model will be too simple. So you will average everything out, which is a bad prediction. But then if you make too many options, you don't never have enough data. So contextual models are kind of a good way forward here. And the goal now is, how do we do both context and models together? And then finally, the next step, and I'll just do this very briefly, is we need to combine this, and we've heard this already in the previous speakers, so we need to combine this knowledge and learning. And this can be that we learn directly from the concept of what is an addition and looking at images, which is knowledge and data at the same time, to really integrating complicated physical formulas just in our learning. So where we have a neural net, but we know that there are physical relations between all these parameters on how they behave. The problem is we never push them in the neural net because it's too difficult how to do this with backpropagation. But we now see more and more of these techniques that actually can translate this and get us better results with less data again. And that was the goal from the beginning. Less labels, less data, less work. And that's all for me today. So thanks.
All right, thank you, Wannes. So for our final presentation and our final two speakers, we have Jonas and Jeroen van der Donckt, and they're both researchers at the UGent-IDLab of the University of Ghent. And they share the same DNA, is what they told me. So they have an interest in time series. And as we've seen in the previous presentation already, we know a little bit what time series are. And more specifically, what they looked at is at how to extract useful information from time series data, and then how to also visualize this. And for that, they worked on 2 open source toolboxes, which I think are freely available. Python, I think, yes. So the first one is TS-Flex, and this is really about extracting information from your time series data. And the second one is Plotly Resampler, which is about visualizing your data in an easy way. But I'll let them explain, and I think they have a brief demo as well. So once they're set up.
Okay, today we will be talking about data wrangling on time series. The format of this presentation will be that we will first highlight some challenges with existing open source toolkits, and then based on that we will present 2 rather new open source toolkits from which we are both the core contributors. I think it's a great place to start off with the definition of what is a time series. A time series is a sequence of data points that occur in successive order. For example, heart rate, which is an unevenly or irregularly sampled time series by nature. Also CO2, very relevant in the last 2 years. Temperature, which can be both from a machine as a human. Asset prices and occupancy, and many more. And the second key component of this talk will be data wrangling. Data wrangling is a process that concerns itself with going from your raw data to your tidy data. Data wrangling itself consists of many operations, such as transforming your data, cleaning it, enriching it, even merging several data files into a larger data set. And once you have your tidy data, you can perform some downstream tasks, such as insights, for example, visual analytics, or doing some modeling. And throughout this whole data science-like procedure, we believe that exploration is an essential part. It goes from looking at your raw data to visualizing your predictions. And during this talk, as I've said before, we will present 2 packages. TS-Flex is a package that focuses on data wrangling, and Plotly Resampler will focus more on visual exploration. And we'll start off with Plotly Resampler. So we believe that visualization is a key part of exploration. It is important throughout the whole data science pipeline. There's a common saying among data scientists that the human eye is the most valuable data mining tool there is. Visual analytics can be used to visualize your raw data and perform an exploratory data analysis. You can then visualize your process data to assess the quality of your processing. You can even look at your extracted features over time, or even the distributions of those. And finally, it can be used to visualize your predictions and your modeling. As we are both data scientists and researchers, we've came up with a list what is for us an effective time series visualization toolkit. We believe that such a toolkit should be integratable in your conventional data science pipeline. Also, we believe that it should support interactive visualizations. It is in our human behavior that we first want to get an overview of the time series data and then want to select, interact, and zoom in into it. We also require that such a toolkit should scale to millions of data points, as time series data tends to be rather high dimensional. And finally, we want it to be highly configurable, as each use case has its own specific requirements for creating meaningful visualizations. And of course, as any tool, it should be convenient to use. So if we look at the current popular Python visualization landscape, we see that no library meets all these 3 requirements. Matplotlib does not serve out-of-the-box interactive visualizations, whereas Bokeh and Plotly do so, but they do not scale to larger data sets. So most requirements are met, But no tool supports both interactive behavior and scales to larger data sets. Hence, Plotly Resampler was born. Here we see Plotly Resampler in action. In this demo, more than 110 million data points are visualized. We see that we still have the fully interactive behavior of Plotly. We can zoom out, we can reset the traces, we can toggle traces, and we can visualize different time series data. For example, on the bottom, we visualize time index data with the time index on the x-axis, and on the right, we have a sequence index. So now that you've seen how Plotly Resampler works, let's explain what happens under the hood. Basically, it's a wrapper for Plotly figures, making it very convenient to use. And what it does is that it adds data aggregation functionality to those figures. It does so by creating a separation between the front end, where the view is shown. The view that is shown is basically what you saw on the previous slide. And in the backend, you have a Dash application running where all your data is stored and contained. And the interactivity between both is realized via optimized callbacks, which are basically methods that fire when a certain front-end interaction takes place. In this case, it is a user graph interaction we are talking about. So we've seen that Plotly Resampler scales to larger data sets, but we've not yet shown that it integrates in conventional data science environments. So this is an example. This is the demo example in Visual Studio Code. This is a more advanced web application for data analysis and assessing the quality of an ECG signal in a Jupyter Lab. This is a visualization to perform, to analyze some processing of an electrodermal activity signal in PyCharm. And this is a demo in Google Colab. So with these few lines of code, we are able to visualize 110 million data points, and we only have the front-end view on your local computer, whereas the data still resides on Google its servers. So to conclude, once we empower Plotly with Plotly Resampler, we see that all the requirements are checked and effective time series visualization can be realized. I guess I'll hand the mic over to Jonas now.
So now that we're able to gain insights in our data by empowering our data visualization with Plotly Resampler, you might want to act on those insights. So we've landed at the data wrangling part. So time series data wrangling can be seen as three main things. First, you have time series processing, which is, to our opinion, rather convenient to realize. Time series processing can be seen as a pipeline of 2B sequentially applied processing steps. These steps can be filtering your signal, resampling your signal, or decomposing or composing your signal of multiple signals. And then next to that, you have time series feature extraction. This is a step of reducing your high-frequency time series data in a lower dimensional feature space. Most often, for classical machine learning problems, this boils down to strided window feature extraction. And lastly, you have chunking. Not all time series have time series data all the time. You can have gaps. So what do you want to do to have intended behavior? You want to chunk your data so no gaps occur in your time series. Now, when we zoom in more into the feature extraction process, we see two main requirements. We want to have a strided window definition format, and possibly we also want to define multiple window stride configurations. To make that a bit more concrete, I'll show you now an example. So here, let's suppose that this is a heart rate data example, and we want to summarize this data in a lower dimensional space. So we will extract features using a window strided definition format. So here we have a single window which is shifted twice with a stride step size. But suppose you want to analyze a heart rate, whether it's anomalous or not. Maybe this window is too small and you need to have a larger temporal context. So you want to add another window, which a larger window size, to have more temporal information in your feature vector for that representative time step. So next to this, we also want to have that these time series toolkits do not make so much assumptions about the sampling regularity. Think about the heart rate data again. If your heart is beating fast, like mine is now, the data points between successive heartbeats will be short. But when it's beating slower, each successive heartbeat will be spaced more from each other. Additionally, as Not all data types are numeric. You can have string-like, categorical, bool-like, or even time-based time series data, like time to complete an event. So time series toolkits should also be able to support this data type. And lastly, each data science toolkit should support some form of integration with other data science packages and naturally be convenient to use. So when we look at the time series toolkit landscape, we see that most tools meet the basic requirements like built-in feature functions and a strided window definition format, but when we move towards the more advanced requirements, we see that few of them support some of these requirements. This highlights the need of a toolkit which can support these requirements. So hence, we created a new baby, the TS-Flex. TS-Flex stands for Flexible Time Series Processing and Feature Extraction. It has no built-in feature functions, and this is because our philosophy is that we do not need to re-implement the wheel, but just integrate with processing and feature functions from other packages. So TS-Flex can use feature functions which are listed in TS-Fresh, TS-Vel, Scikit-learn, NumPy, SciPy, or Stotz models, and many more. Additionally, in TS-Flex, you're able to define a multiple window stride combination in a holistic manner, and it does not make an assumption about the sampling rate or data alignment, or even the data type. And lastly, it also supports chunking. So now let's add the icing on the cake. When we compare TS-Flex to the other eligible feature extraction packages and we use TS-Fresh on a strided window feature extraction benchmark as baseline, we see that TS-Flex is over 200 times as fast as TS-Flex, and when looking at the memory consumption, TS-Flex uses more than 2,000 times less memory than TS-Fresh. So when we now look again at this table, we can see that TS-Flex meets all those requirements. And so we hope that the monthly installs will keep on rising. And now to conclude, your data wrangling, operations, and insights can be improved for large time series by using both Plotly, Resampler, and TS-Flex. We hope that we sparked your interest in both of these packages and gave you some food for thought during lunch, so you can, play around with these and look at our documentation. At last, we have a small demo where we demonstrate how both these packages can be used on a sleep staging example, and I will give the mic back to Jeroen, as I will handle the PC.
Okay. So you are seeing? Yeah, awesome. I guess we'll first load the data just. Yeah. That's not of interest, I guess. Some properties about the data. The data is rather high dimensional. So we have 4 time series. 3 are sampled at 100 Hertz, and 1 is sampled at 1 Hertz. In total, this adds up to more than 7.5 million data points. And first, we'll create an exploratory data analysis plot where we will visualize the time series together with the labels being the sleep stages. So this is a plot that was just rendered now of more than 7.5 million data points. We can conveniently zoom in over the shared x-axis and do a more in-depth analysis of those time series. And now we'll do some basic feature extraction. We will leverage the features from Scikit-learn. So we have just a wrapper that wraps the whole package basically and then integrates all the features. On several windows with a stride of 30 seconds. Why 30 seconds? That's just a convention in sleep staging that every 30 seconds a new label is given to the data. And we have the larger windows, as Jonas said, to add more temporal context to our feature vector. So these are basically a printout of all the features that we will extract now. And now we'll do the extraction itself. And yep. In 2 and I think it will be 3 seconds, we've extracted 126 features on all this data. And the nice thing is that with TS-Flex, as it maintains your time index, you can now visualize again these features on top of the raw data and your labels as well. So for example, now we've selected the EMG column, which is like some movement signal. And if we look at, for example, the root mean square feature, we see that it kinda resembles properly a more smoothened version of your signal, but it's actually also quite predictive for the outcome. So yeah, this is how Plotly Resampler together with TS-Flex can empower your machine learning pipelines on time series.
Jeroen nog iets zeggen van tijd realiseren of zo.
So that's it for this session. I want to... yes, yeah, of course, questions, obviously. So first I want to thank the speakers again. It was very interesting. And I'm sure some of you have questions. So maybe we can ask questions for the three presenters. So if one of you has a question, go ahead, feel free. Let me start off with a question maybe then. I guess the first question for a Plotly Resampler, because I'm actually quite impressed by how fast it is. Is it really that you, like the underlying technology is you resample, like you don't show all of the data points or?
Yeah, so when you have like more than 2 million data points, if you would plot them all in the front end using such few pixels, not all data points are as relevant. So you can perform a data aggregation method. There are various data aggregation methods, and we use one of these various data aggregation methods to plot that. But what we also do, we use a custom component with optimized callbacks to only send the data which needs to be updated to the front end. So by using both these techniques, like a C implementation of our data aggregation method and those optimized callbacks, we can make it really snappy and interactive and like enable to visualize more than 110 million data points really snappy in your development environment. So this is really powerful. Yeah,
thank you. It's quite impressive. Maybe to tie into that, a question for Ilkka. In your, like, because you presented at some point a slide where you show that ML is just only a very small part of the whole pipeline. In your opinion, how does visualizing the data and interacting with that and understanding the problem, how does that tie into the whole pipeline? And do you know whether it's possible to build better tools around that?
Well, even if it's a small piece, it's actually a very important piece. And secondly, when we are looking at the MLOps world, we are talking about huge data sets like terabytes, petabytes, and this kind of tool can be fantastic if you have a data lake with, actually that's the use case for it. If you have just 2 kilobytes, it's not so useful. So I think it fits fantastically. Actually, I have a quick question because I have been brainstorming and working on like an annotating system that the machine learning model is part of it, so that it shows you the things that it's most confused about, so that it doesn't. I would love to try to integrate that to this, so maybe that's a direct result. Yes.
All right. Any questions from the audience at this point? Yes. Maybe if you can speak loudly at.
Okay, so I think the hottest word is something called Kubeflow by Google, but it's also Kube comes from Kubernetes, and it's infamously difficult to get running. There was a nice podcast that Kubeflow is all the rage, but nobody knows who is using it because it's so complicated. For example, I use personally, currently I'm a bit like a vendor block because I'm using Azure. Azure has all the big cloud providers have their services, so any of them, all are good. And then what I'm doing currently is then you can make your cloud thingy like an agnostic, so the ML flow that I meant is maybe one of the more bigger old school sure winners. But yeah, it's like a JavaScript front-end world that there are so many competing technologies, and if I now mention something, then I will be butchered. So. But my advice would be just there are many good ones, and don't worry about the struggle, just pick one and learn it, and usually all of them actually are solid. The big names, MLflow, Kubeflow, any of the big cloud providers.
Thank you. Any other questions? Yes.
It's not really a question, but I wanted to compliment two guys there. Sorry, with the names, I'm horrible.
Jeroen and Jonas.
Yes. For developing something and giving it to the community open source, and it really requires a lot of effort and struggle, and I know a little bit about it. So
I think we should also thank the university for that, because they give us the opportunity to do this. So I think it's just a nice collaboration of everyone in there.
That's really cool. Thanks.
Thank you.
Are there any constraints when using the wrapper of TSFlex?
Wrapper of TSFlex or Plotly resample? TSFlex is
resample,
well, it is a web application, so it starts at a port. So if you're working remotely, that port needs to be forwarded towards your local view of the Jupyter in some way. So that's a limitation, but it's in our docs normally. And
you can wrap any Plotly figure, so that shouldn't be a limitation. I think one limitation is, like a big limitation of Plotly is that the constructor of any trace, so for example go.scatter, is really slow. So you do not want actually to add your data there. And we've created a fix for this, as you can create an empty trace. For example, you can show it in the code, I guess. So we add no data for X and Y, because this calls the slow, the slow constructor from Plotly will get executed by this, but we add it as a high frequency data, so high frequency X and high frequency Y as a wrapper around the add trace method. So that's one, not constraint, but something you should keep into mind when you're playing around with large data sets. But like if it's a smaller figure with 1 million data points, then you can just wrap it and it will go rather quickly out of the box. And of course, also the .show method will show one resampled view that is not interactive. You should call .show dash to really connect with interactive application that is running in your backend.
So when you're working remotely, you should forward now port 8051 towards your local.
But for example, we use Jupyter Dash and several IDEs such as Google Colab. It does this automatically for you. Okay, I think this is it.
Other questions? All right, then we can finish here. And the speakers will be available still, so if you still think of something, yes.